If you connect too many computers to a single shared wire, communication on that wire will eventually fail. When dozens of machines attempt to transmit data simultaneously, their packets collide so frequently the network enters congestion collapse, where throughput drops to zero. Layer 2 switches solve this local saturation problem. By using dedicated hardware ASICs to read media access control, or MAC, addresses, a switch isolates each port into its own dedicated collision domain. But Layer 2 switching has a technical ceiling. While collisions are contained, broadcast frames, messages sent to every device on the network, are still forwarded out of every port. In a massive switch network, the sheer volume of broadcast traffic will eventually exhaust the processing cycles of every connected device. To maintain performance as a network grows, we need a definitive physical boundary to isolate these broadcast domains. That boundary is the Layer 3 router. A router operates at the network layer, utilizing IP headers rather than MAC addresses to direct traffic. By doing this, it stops broadcast traffic at its interface, effectively breaking a large network into distinct, manageable segments. With the network divided, a new challenge emerges. These independent routers must now figure out how to discover the optimal path across a decentralized enterprise to deliver their packets. This table compares common routing protocols. Early distance vector protocols like RIP version 1 and 2 are limited by a strict 15-hop maximum and slow convergence times, making them unsuitable for large-scale environments. Open Shortest Path First, or OSPF, was designed to overcome these constraints. As shown in the OSPF column, this protocol abandons hop counts entirely. Instead, it calculates paths using a metric based on link bandwidth and supports an unlimited number of hops. This capability requires significant CPU and memory overhead. Before OSPF can route a single packet, it must utilize a rigorous state machine to build a perfectly synchronized mathematical map of the entire network. Unlike simpler protocols, OSPF routers do not blindly broadcast their routing tables. They must first form verified relationships called adjacencies through a series of specific states. The process begins in the down state. A router attempts to find neighbors by sending a multicast hello packet to address 224.0.0.5. When a neighboring router receives that packet, it logs the sender's router ID. The connection has now entered the init state. The receiving router replies with its own hello packet. Once both devices see their own router IDs listed in the neighbor field of these packets, they transition into the two-way state. If these routers are connected point-to-point, they proceed, but on a multi-access network, like a shared Ethernet LAN, multiple devices occupy the same broadcast segment. To prevent redundant update traffic across that shared segment, routers in the two-way state hold an election. They designate a single router to manage updates, the designated router, or DR, along with a backup designated router. Reaching the two-way state confirms bidirectional communication and establishes leadership. However, at this point, no actual network topology data has been exchanged. This diagram outlines the synchronization process. In the X-start state, the routers determine a master-slave relationship to coordinate the sequence numbers for the upcoming data transfer. Next is the exchange state. Here, the routers trade database descriptor packets. These contain only the headers of their Link State Advertisements, providing a summary of what each router currently knows. The routers compare those summaries against their own records. In the loading state, they issue link state requests to ask for the full details of any missing or more recent information. This culminates in the full state. Both routers have successfully updated their link state databases to be completely identical. The execution of routing algorithms is strictly prohibited until this full state is reached. This lockstep process ensures that every router on the segment is working from a uniform, synchronized view of the network. So what specific data structures actually populate this synchronized link state database? The database is built from Link State Advertisements, or LSAs. These are the core data packets carrying the granular routing and topology information. This terminal output shows a real OSPF database. Type 1 is the router LSA. Every OSPF router generates one of these to advertise its directly connected interfaces, identified here by specific link IDs. Type 2 is the network LSA. This is generated exclusively by the designated router to represent all of the routers attached to a specific multi-access network segment. While Type 1 and Type 2 LSAs provide a high-resolution map of a local area, Flooding this level of detail across a massive enterprise would exhaust router resources. This is why OSPF utilizes a hierarchical design. In a flat link state network, if a single interface fluctuates, every router in the system is forced to continuously recalculate its entire topology table. This creates a wave of update traffic that can destabilize the global network. OSPF's architectural solution is to segment the network into localized areas. All of these must connect back to a central backbone, known as Area 0. The nodes connecting these standard areas to the backbone are called Area Border Routers, or ABRs. Returning to our database table, ABRs do not forward raw Type 1 or Type 2 LSAs. Instead, they condense that local data into Type 3 summary LSAs before passing them into the backbone. By summarizing routing information, Area 0 and its ABRs act as architectural firewalls. They contain local topology changes within a single area, preserving the stability of the global network. Networks often need to ingest routes from outside their own system, such as internet routes learned from external protocols like BGP. Autonomous System Boundary Routers, or ASBRs, inject these external routes. They do this using Type 5 AS external link states. Because external routes can be numerous, administrators can configure stub areas. These areas block heavy Type 5 LSAs to save memory on lower-end routers, using a single default route for external traffic instead. The not-so-stubby area, or NSSA, is a specialized stub that allows for the injection of specific external routes using a Type 7 LSA, which the border router later converts into a standard Type 5. This system of LSA filtering gives network engineers granular control over memory consumption and CPU load on a per-area basis. With the link state database synchronized and organized, the router must now process this map to find the best forwarding paths. It does this using Dijkstra's shortest path first algorithm. This is the mathematical engine that calculates the network topology tree from the router's own perspective. OSPF assigns a metric called cost to evaluate these paths. The algorithm divides a reference bandwidth of 10 to the 8th by the link's actual bandwidth. It then traces the path with the lowest cumulative cost. The algorithm's output is a loop-free shortest path tree. This resulting map is injected directly into the router's active IP routing table to begin forwarding packets. While OSPF requires complex state machines and a specific hierarchical design, it provides the enterprise with a highly scalable architecture, precise metric control, and rapid convergence across thousands of nodes.